Hello everyone, welcome back to the series. In this part we're going to be doing cross-validation. So just a recap of the whole series, we looked at the array, then we went into the vector, looked into the time series, which is essentially represented by a vector. Then we looked at matrices, so we can represent multiple time series, which we call multivariate time series. And then the previous videos, we looked at the model, and we looked at both as a regression and as a classification. And now this is all about making sure that the model that we've trained is robust and reliable. And this is the subject of cross-validation. With cross-validation, there's actually multiple ways. There's like multiple ways to skin a cat. There's multiple ways to cross-validate our time series data. You just got to be very careful though. If you just like use, I think it's like k-fold, for example, we always want to preserve the time correctly. Remember, we want to keep things in what's called temporal order. So we just got to use some cross-validation methods that are specific for time series data that still preserves the temporal order. Anyway, so that's all out of the way. So the key goals of this video is to show how to get more reliable and robust estimates of how well a machine learning model will perform on new unseen data. I've had quite a lot of people come with comments that they tried my model, but they tried it with different test sizes and they get completely different results when they changed it for, like, say, new data points, or changed the train and test size split. And this is what we'll look into as well. Like, okay, how can you make your model more robust and less sensitive to an individual train test split? So the first thing we're going to do, and also as well, another goal is that we're going to compare the model performance using the different cross validations to see which one is better in this case. And there's no such thing as like one is better than the other. It really depends on the distribution of your data and other variables. Okay, so the first thing we need to do, as always, is to import our libraries. I don't think I need to go through each one individually, so I'm just going to let that run. It's just going to take a while because it's just starting up the kernel. So this is the problem that we're trying to solve in this video. Is that, for example, if you change the train test size ratio, it can be your performance can be very sensitive to it. So we want like a more robust method to ensure that our model performs well on new unseen future data. So this is the classic time series split. So for example, we always use like the oldest data for training and the most recent for test. So we never mix, like, for example, T5 within like here. So it's always preserving the time order. And the main reason for this is because of, like, we don't want any what's called data leakages. We don't want it to train on data it hasn't seen. So that's why and this is like in classical statistics, this is called like in sample, out of sample. So what we want to do is, I want to just show you, just like sort of visually with ASCII art, is the expanding window. And let me just put this in here. Expanding window. And the expanding window is where essentially we increase the window size, the training size for our train set. So I'm just going to copy and paste this. And there you go. So you see a much better visualization. So you see, for example, in the first fold, our test size is like two. There's 2 data points in here, okay? And then for the next one, it increases, right? So for example, here it's now increasing like from T1 to T1 to T4. And we're also just moving as well, as you can see, the window as well. So it's like a sliding window, but we are expanding the window each time. So this is what's called expanding window, because the training window size is expanding. Okay, and now I just want to quickly just show you again, using the power of ASCII art, is the rolling window. And again, there's no one better method better than the other. It's purely just based on several factors, mainly like the distribution of your data. Okay, so I'm just going to copy and paste it in here. Okay, and as you can see here, in this example, the training and the test window size is fixed, but it's just sliding across, rolling across, right? So it starts with the first 2 data points as training, and then the next 2 data points as testing. And then for the next fold, rather than being T1 and T2, it's now T2 and T3. And also the test hasn't changed the size, but it's just changed which data points. And as you can see here, it's not mixing train and test data. It's just always purely the train's the oldest data set, and then the test is the most the future data set. So that's the rolling window, right? And these 2 combinations provide you a good way for finding like a robust and reliable machine learning model. So now what we want to do is, rather than just we can actually start building, and we're going to create by hand the expanding window and the sliding window. And there's also another one as well, which is we're just going to vary the time series split. But the first thing we want to do is just to load the data. So I'm just going to make a comment here, is that we're going to load the data. So again, we're going to still use the same data as we have done for the previous videos. And I'm just going to copy and paste. And just in case you're watching this video from the start, and you haven't watched the previous videos, that essentially this data is just Bitcoin dollar, what's called the perpetual future contract. It just allows you to easily speculate up or down. And this is like 1 hour time series. So each row represents an hour time interval. Okay, and it's just standard open, high, low, close prices. Okay, so now we've loaded it. So this should all be muscle memory now to you now. So the first one we need to do is to create the log returns. And if you're not sure what log returns are, I recommend to go through the previous video so you're in sync and ready to watch this video. Okay, so that's our closed log returns. And now what we want to do is to create the lags, because we're going to be using an autoregressive model. Okay, so now we've got our log return. So that's what we're going to be predicting. And these are the inputs that we're going to use to predict, which we denote as the features. And now what we're going to do, because we're going to be looping, training lots of models all the time, and I don't want to copy and paste code. So what I'm going to do is I'm going to the training loop that we've been using so far, I'm going to create it as a function so we can reuse it and don't. This is really good software engineering practices that you should, if you see yourself copy and pasting code, change it so it can either be as a function or in a class, or just so that you don't have to copy and paste. So I'll just make a note here, so create training loop. And maybe I'll just quickly go over what it's doing, let me just copy and paste this. So I'll just briefly go over, because I've done it in the previous videos. So essentially it's the PyTorch training loop. It's just looping this number of times, which is the number of epochs. It's what's called a full batch gradient descent, which is good if you've got a very small data set that you can fit into memory. And our data set's small enough that it can all fit into memory. But obviously, if you were like working with tick level data, like getting rows essentially multiple per second, and with a large, let's say a long historic data, then this is not feasible. But just with a small time series that we have, then this is definitely feasible. So we essentially we reset all the gradients because they're accumulative, so we always want to reset them to 0. Then we make the predictions, which is called the forward pass in machine learning. We compute the loss, and we choose the function to quantify the loss, and then we do what's called this back propagation, which is to compute the gradients with respect to the parameters. Because it's a logistic regression, then it's just our weights and our bias, and then we update the model parameters using the gradients, and then just for debugging and just for it's useful to print out like every iteration, just so you can see how the training is doing, if it's like the performance, like the loss is not increasing, or if it's steadily increasing. And then we've added this. Oh, this is another important thing, is I've added this verbose equals true flag, and that's just if I want to essentially just print out these statements. So because later on you'll see that it will just be noise. So so that's just that flag, and it's by default it's true. Okay, so that's the loop, and now what we need to do is to, like, this should be bread and butter to us, which is to create the time series split functionality. Series split, and I'm just gonna because I've got this. We're going to copy and paste just to explain why we're doing this, but this should be, I think I've covered this multiple times in this series. So remember, essentially it's just to keep an in sample and outer sample that preserves time order. Let's not be plural. Okay, and now I'll just show you the code. So it's exactly the same code as in the previous videos. We have a default of like 75, so essentially saying that 75% of the time of the data should be used for training. So the first 75% of the data is used for training, and then the remaining is used for test. So the train is our in sample, and then the test is our out sample. But we'll just keep to machine learning terminology here. So we'll just call it train and test set. And the first thing we want to do as well is just to empirically check that it's split correctly. So maybe if I might just copy and paste this a bit quicker. Okay, and so the first thing we need to do is just to check our trained data set, just to see the timestamps on them. So, and then we also want to check. Okay, so you can see here it starts from 2020 and it ends in 2024, 5th, 17 at midnight. Okay, so now we just want to check here. So you see here that it starts correctly because it's the next time interval is in 1 hour's time, so that's correct. And you can see this is until the 11th, so that's correct. Okay, so that's the underlying data. And now what we want to do is to actually start training the ML model. I just wanted to show you how we can use that function to do it. So what I'll do now, train ML model, and what I'll do is I'll maybe just copy and paste because it'd be quicker. Okay. So I'll let this run. So maybe while it's running, I'll just go over what it's doing. Okay, so we're specifying our features, which is the auto-regressive lags. Pardon me. And then this is our target, right? So we just say the number of features. In PyTorch, this is our linear regression. So this is essentially the mathematics of it. And so we specifying the number of features, and it's only got one output. We're going to use the Huber loss, which is a nice balance between mean squared error and moving absolute error, the mean absolute error. So it's just a nice balance in between. And then the next part is the optimizer. So we're going to use the SGD, and then the number of training iterations, we're going to use 5,000. And because PyTorch expects all the data to be in tensors, we need to move the data into tensors. And then we click on we run this functionality. So we pass in our model, pass in our loss function, we pass in what the optimizer we want to use, and then we pass in our data that we split manually. And so we see here, okay, this is the weights that it's learned. And so now what we want to do is to retrieve, we want to get the predictions for the outer sample, which is in the test, right? So maybe if I just I'll write it here. And the code for this, and also we're going to be wanting to know the test prediction, so we'll make it into a function as well, because we don't want to be copy and pasting things all over the place. So let me just run this now. So you see here, this is a really important thing. We're going to get back a two-dimensional tensor. So we want to change the shape. So that's it, the two-dimensional tensor, and we want to reduce it down into a one-dimensional tensor. So this is what the dot squeeze one does. And yeah, this is, I recommend if you don't understand what this is doing, just to put into ChatGPT. Essentially, we put it in evaluation mode, so it makes it more efficient. Like for example, if this was like a neural network, then it wouldn't run, it might have some layers called dropouts, which are sort of like a form of what's called regularization, making your model less sensitive to noise. But yeah, this is totally out of the scope, but we'll see later on, maybe in the series or in future videos, why this is useful, but maybe definitely not in this video. Anyway, okay, so these are the predictions, right? But what we want to do is put it back into our data frame so we can do analysis. So that's what we're going to do next. So maybe if I just explicitly write what we're going to do. So this is essentially our y-hat, and if you watch the introduction video, then you understand what the y-hat is essentially saying what are predicted values of what we want to predict. We want to put them into here and then compare them against what was at the actual values. So just to make it very concrete, that these are, the y-hat is our predictions, and then the actual values is what we're predicting is the closed log return. So we want to compare closed log returns against y-hat. But there's another, essentially these loss functions, you know, for example, we're minimizing these loss functions to reduce the error, right? But it's Huber loss, it's mean, like I said, or let's just say it's mean squared error. We're just reducing the squared differences, okay? But we need to evaluate, that doesn't, we can't interpret if the model is profitable or not. So we really need to evaluate the profitability of the model, because the mean squared error or the mean absolute error it's not indicative of the profitability. So let me just put this, make this as a header. So now we need to evaluate the profitability of the model, and I'll just make a note. Okay, and we're gonna, again, we don't want to be copy and pasting the code everywhere. So what we're going to do is we're going to factor it into a function, and this is the function. So maybe I'll just quickly go over. Okay, so it's called eval profitability. So we pass in the model, we pass in our test, and it's important that we pass the test data set, and then the test input, and then it runs this test model predictions, which gives us our y-hat. Then we put it into the data frame, and then once we've got the predictions, we want to take the sign, the mathematical sign of y hat for each value, and that's going to be used as our directional signal or trading signal essentially, because if it's 1, it means that we need to bet going up. Well, in trading lingo it's called long, and if it's -1 we need to go short, which is trading lingo to bet the price is going down. And then we need to just calculate the trade log return, so the how much money we would make in log return space. So we just essentially, it's very simple, we just need to multiply the directional signal multiplied against the closed log return, and then essentially this tells us if we make money or not on each individual trade. And also, just because the log returns are time additive, we can take the cumulator sum, and that represents our equity curve. And then another just a useful metric is like, did the trade win or not? And then it's a simple predicate that we just test that if it's greater than 0. But the most important thing is we want to know what the expected value of our trade is. So this, obviously, if it's positive, then this means on average each trade we make money, and so that's our metric for our cross validation, is the expected value of the trade log return. Okay, so maybe if I just run this. So this tells us that we have a positive EV here. So that means that if we trade this, that we'll make money on each individual trade. Not maybe. And then, for example, once you've got the law of large numbers kick in, then this is where the expected value kicks in. So now what we need to do is to, we want to put this all together, right? Because we're going to be, we don't want to be manually copy and pasting all the code together. So this is what we're going to do. So going to create a function to evaluate the model's profitability. So it's going to train the model and also then get the test predictions and then evaluate the profitability of those predictions. So essentially we're just wrapping up all that we've done together. So this is the code. Maybe if I'm just going to make a note here, just so if you go to look at it, that you can understand what it's doing. Okay, so that's our function. So now we can easily pass in, maybe I just say what again, it's just you're passing in our train data set and our test data set, and the size of this depends on our heuristic for the cross validation. So this is sort of to make it generic, so we can try this with the rolling window, expanding window, and the time series splits. And then, so it's essentially just the code that we've just been building, but just wrapped all together. So I recommend to go over it just to see what you're doing. Okay, and now first thing we want to do is just to experiment with one of the cross validations. So one of we're going to do is to do this. So we're going to try it with different train test splits. Okay, so what we're going to do, I'm just going to make it very clear what we're doing. So we're going to define, and I recommend for you to try and change the features here and to experiment. So what I'm doing is I'm implicitly defining an autoaggressive free model. So in the previous videos, you should know now that what an autoaggressive model is. So essentially we're just looking at the three previous lags to predict the closed log return. And so now let's just try it with like different splits. So for example, I'm going to try with just, with the train size just only being 0.4. So that the remainder is used as tests. So there's more test data than is training size. And I'm just going to do this like just manually, just to show you. Okay, what about if it's like a 50-50 split? So you see here that it's all positive EVs here, but of a varying degree. And I'm just going to do this, just increasing each time. So now I'm just going to put 0.7. And you can see that so this seems to be not so sensitive, this model, to the varying the train size. But now let's just try it with 0.8. Okay. Okay, and so if we use the train size of 80%, leaving 20% left for testing, then we get a negative EV, so we don't have an edge here, whereas with the previous ones we do have a statistical edge. And now let's just try it for 0.9%. Okay. And I just thought I'd go up. In practice, you would never go up to like 0.8 or 0.9, but just out of curiosity, I was just very interested to know. Okay, so we've got some figures here, and so we've got a negative edge when the train size is like over 80%. And now what we want to do is so we've done that manually, right? It would be very painful if we had to go manually and to do this like what I've just done now. So using the power of programming, we can just build our first cross-validation loop. So this is what we're going to do now. Okay. Okay, so now this is the loop, and I'm just going to run it, and while it's running, so essentially I'm just looping over train split sizes, and I'm just splitting the data by time, and then I'm just evaluating the model profitability, getting the expected value, and then I'm adding it into this array here, and I'm also adding the train size as well, and then pardon me, and then I'm just putting it together. In computer science, you call this concatenation. So I'm putting it all together and put it into a data frame, because then it just makes it very nice to display the underlying date results. So now I just print it out, so I can see that this is essentially what I've just written below, but just in a more presentable way, and then without manually looping. Right? Imagine, like for example, my delta size here was 0.1, but imagine if I wanted to do 0.05 or 0.01. I had more fine-grained delta size, then there'd be even more copy and pasting essentially. So we're just automating it, and you can see here. And now what we want to do to get the cross-validation result is just take the mean of the expected value to see, okay, if how robust is this, like to different training sizes. And we can factor this in now. So this is it's telling us that it's positive on average. So this tells us it's quite robust to the changing the training size. Then you could even argue that we can actually remove these two, because we would never like go over or if we definitely love, for example, 90%, but it's your preference essentially. Okay, so that's the cross-validation of time series splits, but now let's look at some other methods, and more specifically let's look at the rolling window cross-validation. So maybe if I just mention this, put a header for it. Okay, and now what I want to do is I just want to print out just to show you the underlying algorithm behind it. Okay, so there's 4,344 rows, and I'm just going to use this. which is like just hours in a month. I'm just approximating that there's 30 days in a month. Now, then I just want to know the ratio, because that will tell me the window, the number of windows. And okay, so now I want to do is to do this. I want to loop. I just want to show you the indices of the rolling window, because I think this will make it maybe hopefully more intuitive, like what it's actually doing. So this is the I'm just printing out the indices of the data frame so you can see what it's actually doing. So if I just loop over this, so you can see with the expanding window that the train for the rolling window, we start at 0 and the training starts at 724, and then the testing starts well, actually it's just 725, but because this is an index and we're using the Python indices, that yeah, they're not overlapping essentially, but then we're using the next time window size for the testing. So you can just see here, essentially this is the indices to filter out our training data, or to extract our training data, and this is the indices, start and end indices for our test window. And you can see it's just increasing by 724 for each of these indices. And so this is rolling window. So yeah, I just encourage you to look at this code. And what we're going to do is like just show like maybe a bit more concrete and understandable if I show like an example. Okay, so we're saying that from 0 to 724, this is our training, and then from 724 to 1448, that's our test data set. So, and now we have to look at the underlying data. You can see 724 rows, and if we have a look at test, you can see that it's not overlapping. There's no here. It's the next tick, or we could time interval in the time series, and again it's 724 rows. So hopefully that's more intuitive as to what it's doing. But we want to, and just we can use off, because our function eval model profitability is independent of the algorithm to split the data. We can pass it in. So even though we're now using rolling window, we can still use our evaluate the trainer model and evaluate its profitability. Okay, so I'm just going to let it run, and then let's see what it is. Okay, so it has a positive expected value, but but it's positive, so that's the main thing, right? And so essentially, we can just loop over using the algorithm. This algorithm here, we can then just extend on this to actually make it a rolling window, and this is what it is. So I recommend just essentially just looping over. Like the main important thing is, which we've gone over, is the calculating the indices, and the rest is fairly trivial. Okay, so now that's our eval rolling window. And what I want to do is to pass in the data. Bear with me. I didn't call the function. Okay, so that's, and now what we'll do while it's evaluating, I'm just going to print out the results. And also what we want to do is to print out the average expected value. So we will call this Okay, so here's our results. So this is, or maybe window number is not correct, maybe iteration number maybe. So you can see here as it's rolling that there's a few that have been negative, right? So this is not as robust as the previous method. So, but let's calculate the mean, right? So we see on average that it's positive, just a small positive edge on average using rolling window method. So that's the rolling window, and also as well, just this is you can experiment, and actually this is one of the exercises. Experiment with the window sizes. You may want to increase the window size here or make it even smaller. So yeah. That's just an interesting idea for you. Okay, so now what we want to do is to evaluate the expanding window. Okay, and with the expanding window, I think it'd be better if this should be a bit more intuitive than with the rolling window. You can see, okay, it always starts at 0, for example here, but it doesn't always have to be. You could, there's no fixed rules of how you define your cross-validation algorithm. But say, for example, here it starts with the first window, and then the next fold is that it's the training window is 2 windows, and then it's 3 windows, 4, 5, etc. Right? And the test window is always like of a fixed size of 724. And again, you can customize this to how you want, and that'll be one of your exercises at the end. Okay, so that's that. And now what we can do, so that's the algorithm to calculate the indices. So now we know how to do that. Then we can just put it all together to create a function to do it. And actually as well, what I might do is I'll add this to the public code repo. So if you want to experiment with this, I'll add it into the research API. If you would like this, please put a comment. The more comments that I get, the more possible that I will do it. Okay, so that's the expanding windows CV. And now we're just going to call it. Okay, as that's running, what I'm going to do, so maybe I'll just explain. We're passing the data frame, the features, the target, the window size, and the number of iterations. So that's essentially what it's calculating. Okay, so we're going to print out our result for the expanding window. And now we want to calculate is the average EV. And essentially, just if it's not very clear, essentially what it's doing is saying what's the average statistical edge that we have on each for using cross-validation. Okay, so we run this. So I think this is roughly the same as the rolling window. So now we've used 3 methods of cross-validation. And that's really concludes cross-validation. So just to conclude, maybe just put a conclusion. I want to put that as. So maybe if I summarize it here. Okay, maybe if I copy and paste this. Okay. So this is our sort of conclusion. So, spelling that. Okay, so we've introduced cross-validation, and we've also just shown like practical examples of how to get more reliable, robust estimates, especially if your model is very sensitive to the time series split. And I've showed like 3 examples of this, and also as well, there's no right or wrong answer or method to do cross-validation. It really just depends on your data. So for example, if rolling window is really more, gives you better results, then you want to make sure when you deploy it that you're always using, let's say, I don't know, your window size is like 2 weeks. Then you want to make sure that when you deploy it, you want to use the most recent 2 weeks. And then after 2 weeks in production, then you release your code, retrain your weights. Or you could just even do it on a weekly basis as well. So yeah, that's just some ideas. Okay, so maybe now as well that I will do some exercises just so you can experiment with cross-validation. So I'll leave as exercises the following. So the first exercise is to experiment with the rolling window. Okay. And essentially what I want to do, maybe if I just put this here. Is to do this. So I want you to try and change the window size for rolling window to see if you can get better results. So you don't have to, it can, at the moment I've hard coded it that the train and window sizes are the same, but you could have, like, for example, the train window size is larger than the test window size. Like, for example, rather than, you know, the train rolling window and the test rolling window to be 1 week each, it could be that I don't know, that the train window size is 4 weeks, and then the test is only 1 week or 2 weeks. Just to try and experiment with different sizes and make the window, refactor it so that the train window size can be changed independently. At the moment it's hard coded, so that's quite a good exercise for you to do. Then the next one is to do the following. Exercise 2. We're going to do exactly the same, but for expanding window. So again, at the moment the expanding window is hard coded. So the training window and the test window size are, oh no, sorry, that's not for expanding, it's not. I just want you to oh, maybe if I put this in. I want you to try different window sizes for your expanding window, and also don't do it manually. Write an algorithm to do it, and again, just do like what I did. I just collect all the data and then have a look and see. So I think one of the key lessons here is to automate as much research as possible. Don't be doing this like manually. So if you see yourself, it looks like, okay, I'm copy and pasting lots of stuff, write an algorithm to automate it. Okay, so that's the end of the video. Please like and subscribe, and also your feedback is very important. So please let me know your thoughts on this video. Thank you very much. Cheers. Bye. This series is available for free thanks to my incredible generous supporters on Patreon. My goal is to keep this channel independent from sponsors, so I can create the content I truly believe in. If you feel my work brings you value, please consider supporting the channel by becoming a Patreon member. You can find the link in the description below.